solve the recurrence relation obtained as the answer to exercise 21C of section 5.6. Now we're going to use iteration to solve this recurrence relation to get an explicit formula for this sequence. I should also mention that t sub 1 equals 3, but we're going to use iteration to solve this recurrence relation, particularly because it's my favorite way of solving recurrence relations. The way we're going to do that is we're going to solve for t sub 2 in terms of t sub 1. So according to the recurrence relation, t sub 2 equals 2t sub 1 plus 3. Now I'm going to leave that as is. I'm not going to plug in t sub 1 equals 3, and that's the whole iteration process. We'll do that at the very end after we generalize. Now let's find t sub 3. T sub 3, according to the recurrence relation, is 2t sub 2 plus 3. But we want all of our terms in terms of t sub 1. So I'm going to substitute what we got for t sub 2 into t sub 2 here to get 2 times 2t sub 1 plus 3 plus 3. The next thing I'm going to do is I'm going to distribute the 2. Now I know it's tempting to say that 2 times 2 equals 4, but I'm actually going to write it as 2 squared. And that's because a lot of the solutions to these recurrence relations are exponential in nature. And it's easier to see that if you group together factors without actually evaluating 2 squared. I'm going to write this as 2 squared times t1 plus 2 times 3 plus 3. I know it's tempting to do these multiplications, but I'm only distributing and combining like terms. Now let's do t sub 4. And usually by t sub 4, we should be able to see a pattern. So t sub 4, according to the recurrence relation, is 2 times t sub 3 plus 3. And then we can substitute our solution from t sub 3 into t sub 3 to get 2 times 2 squared t sub 1 plus 2 times 3 plus 3 plus 3. And so now I'm going to distribute the 2 and absorb these factors into the other factors of 2. So that means t sub 4 is just 2 cubed t sub 1. And we get 2 cubed times t sub 1 plus 2 squared times 3 plus 2 times 3 plus 3. And now we can start to see a little bit of a pattern. If I had to predict t sub 5, I would say t sub 5 is 2 to the 4th power times t sub 1, and then plus 2 cubed times 3, plus 2 squared times 3, plus 2 times 3, plus 3. And so now that I can predict the next term in terms of t sub 1, I'm now going to replace t sub 1 with 3. And now we can factor out this 3 since it's a common factor in every single term. And then we're left with a geometric series here where we have powers of 2. Now to generalize this formula, we could say t sub n is equal to the summation. I notice here that the largest exponent of 2 is 1 less than the value of the index variable. And each term is going to be of the form 3 times 2 to the I. And if you've taken Calculus 2, you might have seen how to find a finite geometric series. There's a formula for that. But just to keep things conceptually coherent, I'm going to leave this unsimplified, just in series form, just to show you how we get to this part. And now we can jump to t sub 100. We can plug in 100 here, and we know exactly what we need to do to calculate t sub 100 without having to calculate every single term before t sub 100 first. Thanks, everyone, and I'll see you in the next video.